And welcome to another fun day of chemistry in which we're going to discuss phase changes and how energy is involved in changing these phases. So first we're going to look at phase changes that absorb energy. Now anytime we have energy being absorbed, that energy is called an endothermic reaction. Okay, stop that. Sorry, I'm talking to my computer again. So endo, and you've heard this term before, endothermic reaction. And in endothermic reaction, we have energy going into whatever the system is that we're looking at. So we're going to be focusing on changes and differentiating between what's called the system and the surroundings. And our three types of phase changes that absorb energy are melting, evaporating, and we've talked about sublimation before, melting going from a liquid to a solid, evaporation, vaporization, and boiling is a special kind of vaporization. We'll talk about that in the next lesson. I said liquid to a solid. Try solid to a liquid. I hope you caught me on that one. Then we go from a liquid up to a gas, and then sublimation is when we go directly from the solid to the gas phase. Now, an endothermic reaction, endothermic process is always a cooling process. And that's because we absorb energy. So absorb, there's that energy going in from the surroundings. And in general, the surroundings are going to be things like the air around us, can be you as a body if you're having reactions or things happen inside your body. And the energy that's being absorbed by the process is going into sample. And there's that endo, meaning inside. So when we have this happen, during a phase change, a couple of things happen. So during a phase change, we're going to have the kinetic energy of the surroundings is going to decrease. And the reason for that kinetic energy decreasing, so if we look at the diagram on the right, we've got, in number one, we've got the liquid water molecule has enough kinetic energy to overcome the hydrogen bonding at the surface. So it's going to come through the surface. And as it comes through the surface, it's going to break those hydrogen bonds, and that requires some energy as well. So breaking the bonds requires energy. But there's more to it as well as that. So in addition, what's going to happen is that water molecule that was moving was a fast water molecule. So we removed a fast molecule. And when you remove a fast molecule from the sample, the average kinetic energy, and remember average kinetic energy is temperature, is going to decrease. So the average kinetic energy of the liquid decreases because the kinetic energy of the liquid is going down. Now, breaking the bonds is also called a change in potential energy. And so the potential energy of the water is going up. The kinetic energy is going down. The potential energy of the water is, of the molecules, is going up. And so we're having this transfer of energy from kinetic to potential energy. Meanwhile, the molecule that enters the gas phase has lost kinetic energy because it's overcome those hydrogen bondings, and it's slower than the surroundings. So it's a slower molecule, and the slower molecule decreases the average kinetic energy of the vapor of the air. And so the temperature in the air is also cooled. So the temperature goes down. So let's go and finish out our blanks here. So as the kinetic energy of the surroundings decrease, the surroundings cool. So the surroundings are going to cool, the sample is going to cool, and so all these processes are cooling processes. They remove energy. Now, evaporation happens when you sweat. So as you sweat, the reason you sweat is the water, the sweat, evaporates and it absorbs energy. And where it absorbs the energy from is from you. It takes it from your body and converts that energy, that heat energy of your body, into the potential energy of the molecule and breaks those bonds. So breaking bonds requires, I kind of filled in where I was going to write. Breaking bonds requires energy. You need to put energy in. Oh, and I've been talking about it there. So the potential energy, and that's the energy due to the position. It's like having two magnets next to each other. To pull those two magnets apart, you've got to put energy in. So potential energy is due to the position of the particles. Potential energy increases, and that increases as the particles get farther apart. So we've got to put energy to get those particles farther apart. Oh, that's my whole thing has just shifted around a little bit. That's what's supposed to go down here. So breaking bonds requires that comes right down here. Sorry, that's not what my sheet shows. So breaking bonds requires / absorbs energy. This is what the notes are going to look like. And the potential energy of the particles increases. And potential energy is energy stored. So we're actually storing energy by melting something or by evaporating it. We're storing, putting energy in that can be taken out when the reverse process happens due to the position of the particles. As I said, think of two magnets. You pull them apart, they're breaking that separation, that force that holds them between, and the further apart, gets an increase. Increases the potential energy. So those are all processes that increase the potential energy and absorb of the sample and absorb the energy from the surroundings. The opposite of those are exothermic reactions or exothermic processes. And hopefully you covered these in biology as well. So the opposite of all the above processes, freezing, going from a liquid to a solid. Now is the time for that. Condensation, going from a gas to a liquid, or deposition is the opposite of sublimation, going directly from the gas to a solid. And all of those things are going to release energy. They're going to warm the surroundings, and they're going to release energy from the system into the surroundings. So it goes into the surroundings, and the surroundings are going to gain the energy, and the energy is going out. So the temperature and the kinetic energy of the surroundings is going to increase. Surroundings warm up. So when the system is losing energy, we're going to see that its energy is going to go down and the surroundings energy is going to go up, which is something we have to kind of wrap our heads around, because people want to know, well, why, if we're losing energy, are we getting warmer? Well, it's not the system that's getting warmer. The system is losing a different kind of energy. It's transferring its energy, the positional energy, into the kinetic energy of the surroundings. So on the diagram at right, we have a similar single pane diagram here that's showing a water molecule condensing now. So we got these water molecules up in the gas phase. Now, a faster moving water molecule like the one on the left will hit the surface and is going to have enough kinetic energy to bounce off to overcome the intermolecular forces of attraction, just like with gases not condensing into their liquids, overcoming the intermolecular forces of attraction. But if we have a slow-moving water molecule, it's going to get caught. It's going to have hydrogen bonding, pull it together. So the hydrogen bonding is formed, and the liquid is going to be warmed by the formation of hydrogen bonds. But as before, the gas gets warmed by removal of a slower molecule. So since the gas is warmed, the average kinetic energy, or since the slower moving molecule is removed, the average kinetic energy is going to go up. You're removing something that's slow, so everything else is the average is going up. So the temperature goes up. Meanwhile, we have formed these hydrogen bonds, but also we've gained a higher moving, a faster moving liquid molecule. And because it's faster moving, the kinetic energy is going to go up and the temperature is going to go up. So as the kinetic energy is going up, it's happening because we're absorbing that energy from the formation of the bonds. Forming bonds is always going to release energy. Now, this is a little harder to see when we're talking about things like magnets coming together, because we don't really feel there's a little heat release, but that's not the kind of energy that you can see. If you do take two magnets and put them near each other, if you put them close enough, they'll move together, and that moving together is kinetic energy. And that kinetic energy comes about because they have the potential energy, the potential to move back together. So as we release potential energy, the potential energy of the system comes down, and the overall system then has less energy than it started with. On the next page, I have a diagram that just illustrates the various phase changes and the different kinds of energy changes associated with them. And this just shows on a scale of potential energy on the left, moving up in potential energy from low to high. So low potential energy at the bottom and higher potential energy at the top. Gases have the highest potential energy because they're the farthest apart. And so going from a solid to a liquid, melting needs energy. So moving up, we always need energy. And let's go back to blue for that. So endothermic, we need or we absorb energy. Going down the other way, freezing, condensing, and depositing, those all release energy, release, or what's the opposite of need? I can't think of the opposite of need, so don't worry about it. The following diagrams show what happens when we string all of these phase changes together. And it's a little complicated, so bear with me as I go along and explain what's going on here. So this phase change diagram is also called a heating curve, because what we're doing is we're starting with a solid. So if this is water, and I know it's water because this is a melting point of 0 degrees C, and I'll show you how we know that in a moment. I'm going to start with water at negative 50 degrees Celsius. So we know that water freezes at 0 degrees, and so at negative 50, it's got to be a solid. So all along this upward slope from point A up to point B, the water is a solid. And the temperature is changing as we add energy in. Sometimes we'll see time on the x-axis as well, but all that means is that as time goes on, we're putting in more energy. So as a solid, what's going on is we're warming the sample, and the temperature is increasing because the kinetic energy of the sample is increasing. So whenever we see a change in temperature, we know that we have a change in kinetic energy. And the same thing is going to happen. Here's point C and point D. Between point C and point D, the sample is all in the liquid phase. And again, the temperature goes up. It's warming as we put energy in. And the temperature goes up as the kinetic energy goes up. And finally, all the way to the right here, point E to point F. That's in the gas phase or the vapor phase. Remember, vapor is just anything that is in the gas phase that we usually think of as a solid or a liquid, like water. And again, we're warming as the kinetic energy goes up, the temperature goes up. So what's happening in these flat regions? In the flat regions, the temperature is constant. Let me do a different color. The temperature is constant. Now, you can kind of guess that from B to C, this is melting. We're going between the solid and the liquid. And at B, we have 100% solid at the melting point. And at C, we have 100% liquid. We've turned it from 100% solid to 100% liquid. And in between, we'd have a mixture of solid and liquid. So what's happening here is there's no temperature change. There's no delta T. If you don't have a temperature change, that means that the kinetic energy has to be constant. So if the kinetic energy is constant, what must be happening is that the potential energy is increasing. So we're having an increase in the potential energy as the particles, in this case the water molecules, the particles move apart. Likewise, in this long region from D to E, we are vaporizing or evaporating. Now again, this is really boiling, evaporation. This is boiling, and we'll talk more about boiling in the next class. At point D, we're at the boiling point, 100% liquid. At E, we've converted all that liquid into 100%, 100, not 1,000%, gas. And the same thing is happening. There's no delta T. Since there's no delta T, then we have a change in the potential energy, increase in the potential energy, and we're moving those particles further apart. In this case, we need more energy than melting because we're moving the particles much farther apart. And so that longer run for having to go to the gas phase is because of more energy needed. All right, so one of the features of this curve then is that you can see wherever you have a flat, you have a phase change. And so if you know what phases you're starting at, what phases you're ending at, you know, okay, if I'm starting in solid, as we did, I wanted a different color. Let me redo that. That was solid. And so we're starting in the solid and we're going to liquid. So we know that that must be melting. So this temperature at 0 degrees must be the melting point. So the lower phase change is always going to be the melting point. And up here, when we're going from the liquid to the gas, that must be boiling. And so that's going to be our boiling point. And this is a great way of identifying different materials based on the fact that everything has its own unique combination of melting point and boiling point. So this is a heating curve. Now, what happens when you remove energy? So heating curve, That's our endothermic processes, right? We're going up in energy. Cooling curves. So the cooling curves happen when you remove energy. So the water cooling curve is just taking that and returning and turning it around. So again, this is exothermic processes because we're removing energy. And by the way, the energy unit, we've seen this before. We saw this in light waves, is joules. And in our next unit, in chapter 16, we will come back and use some calculations of joules when we're talking about processes. But for now, we're just going to look at this qualitatively. So water cooling curve goes the opposite way. We'll start at F and go down to E. And so this is the gas phase. Between E and D, now since we're removing energy, so by the way, the gas phase, so the delta T is negative, the T is going down, so the kinetic energy is going down. From E to D, this is our condensation. Condensation, where the temperature, delta T, is equal to 0. So the kinetic energy is constant. But now the potential energy is going down as the particles get closer together. From D to C, and there's this little something here I'm going to show you in a minute. From D to C, this is the liquid phase. Again, we have the temperature is going down as the kinetic energy goes down. Now, from C to B, there's this strange thing that happens. Let me blow this up a little bit so that you can see it a little more clearly. So what happens here is not every liquid does this, and you don't see this every time, but occasionally you will see this. And what you see is what's called supercooling. Supercooling, what that means is that the temperature is below the normal freezing point. But we still have a liquid. And it's 100% liquid. It's all liquid at this point. And the reason for this is that sometimes it's difficult to organize. Let me roll up a little bit. Organize the molecules into the crystal. And as long as you can keep that liquid from organizing, it will stay a liquid. Water can supercool to about negative 40 degrees Celsius. Actually, the same centigrade as Fahrenheit. Celsius and Fahrenheit come together at 40 degrees. And occasionally you can see this happening. Like on a really cold winter day, you can have water that's liquid. When you pick up the water, you disturb it. And when you pick up the water, at this point, we're going to disturb the water and we're going to come back up the curve. So the water becomes disturbed. I know that's weird, like you're annoying the water. So I guess, yeah, think of it like you're annoying the water. It says, okay, I guess I can freeze now. And so now we have from C to B, now we have liquid, but we only have liquid from here to here. I'm sorry, we only have solid. We're forming solid. The solid starts to form. And what it's going to do, because we're about halfway there, it's going to be solid. It's actually going to be a slush because we have solid and liquid mixed. And then by the time we get to B, at B, we're now to 100% solid. And then from B down to A, that's the solid again. And that is going to be the temperature going down as the kinetic energy also goes down. All right, so this is what you need for the homework for tonight. Please make sure you get that done. Have a great day, and we'll see you next time in class.